In this video, we will demonstrate how to determine the availability of equipment with limited processing capacity and non-exponential processing times through the use of phase-type representations of continuous time Markov chains with a finite state space. The context for this problem is xfab, a leading foundry for analog and mixed-signal semiconductor manufacturing.
Hi, I'm Lloyd Wetzel. I'm the president and CEO of xfab Texas Incorporated. xfab Texas is one of a group of locations that is known as xfab Silicon Foundries, and we have locations around the globe in Malaysia, Dresden, Germany, Erfurt, Germany, and our other location is here in Lubbock, Texas. xfab is an analog-oriented facility. We are not playing in the digital realm and not trying to compete down at line widths of 30 nanometers. We're now working in a realm that's from 0.5 to 1 micron here in Lubbock, Texas, and at 0.13 and above in some of our other facilities. We are an automotive-focused organization as well. About 55% of the business we have here in Lubbock is automotive-oriented. Those parts go into things such as airbag controllers, navigation systems, window controllers, engine monitoring components, etc. within the car. So we typically run our manufacturing in lot sizes that contain 25 6-inch wafers. And those lots run through, in a typical process, about 300 steps to complete the integrated circuit. And at any given time, we'll have as many as 100 different process routings that are running inside the factory and thousands of wafers of inventory. The process flow at xfab Texas is what I refer to as a repetitive flow. And by that I mean that the material will flow through specific types of equipment multiple times while we're creating the device. So it may go through a certain piece of equipment as many as 25 times in creating that device. It may go through other pieces of equipment within the line only a single time. A common issue in wafer fabs today is that the capacity is difficult to calculate because static modeling, which is typically used, does not take into account what the variability is in the arrival time of material and the queue time of material and in the real process time of material. So it's frustrating for management in semiconductor companies not to know what the real capacity is because there's a large investment in equipment to be able to run the processes, and then not what your true return on investment will be is very frustrating. Dynamic capacity models can be created, however, they take a lot of time and effort, and they also take a lot of effort to maintain the model even after it's been established, because every time you make a change in the process flow or in the equipment, you have to then go update the model. Also, validating that model is very difficult. It may take 6 to 12 months of real production to actually validate a dynamic model. And so they're not used very often because of the effort it takes to install, validate, and then maintain on an ongoing basis is very costly. A compromise is currently being seen as the best solution for an operation such as ours is to use stochastic modeling, where you have less time than dynamic to build the model, but you have much higher accuracy than you have in a static model. So it's really seen as the best of both worlds. You can improve the accuracy of your predictions, you can take into account the variability in the process and the timing in the process, but not require 2 or 3 people to maintain that model consistently as you run it. So I personally have been attempting to try to understand what is the real difference in the accuracy of the different models, what is the cost difference, and then I can calculate what is the real value of each individual model to our company.
Okay, this is I'm Marcus Borhani. I'm one of the project managers here at xfab Texas. We are looking at our clean room area. This is our photolithography area. which basically where we print the patterns on the wafers. The reason for the yellow light, we have material that they are photosensitive to UV light, and that's the reason for the yellow light. At this process step, what we do, we take the wafers, they have photoresist on them. We expose it, the pattern. A typical device that we build here, they're CMOS or BiCMOS devices. They could have between 15 to 20 layers of masks, and they go from this area to the next area, which is actually the etch process area, where the patterns define where we want to etch out here in the steppers. Okay, this area is our plasma area. The plasma area is a dry etch processing. Basically, the wafers coming from the photolithography area have the photoresist on it, but there are films that they could be oxide, methyl, polysilicon, nitride, that we actually introduce gases into the plasma chamber, and the film is actually etched in the machine. These processes over here, the plasma is what we call mostly a single wafer processing. So that means the wafers are etched and processed one wafer at a time. And depending on the film chemistry, various gases introduced in the plasma environment, and the films are etched in that area. Okay, this is our diffusion area. The diffusion area is a very high temperature processing, where actually the wafers see temperature ranging from 400 degrees C all the way up to 11 degrees C. What the process is actually the dopants are driven into the silicon, forming the junction of a transistor or a diode, or actually films is grown at the high temperature. Behind me, if you look at the one furnace that has a red color on it, that is a furnace that is at the very high temperature processing. The wafers are loaded into the furnace in the quartz glass for withstanding a very high temperature processing.
The fabrication of semiconductors is a multi-step sequence of photolithographic and chemical processing steps involving the deposition, removal, patterning, and modification of electrical properties of silicon wafers. As both the thickness of the wafers and layers in the semiconductor are very small, the work is performed in an environment that is clean, called a clean room, as even the smallest speck of dust or foreign particles can render the device unusable. In addition, numerous electrical tests on the devices are made at each of these steps to ensure proper performance. From start to finish, it takes an average of 6 to 8 weeks to produce a semiconductor. The problem presented in this video is representative of one in that industry, but keep in mind that the problem and all the data given in this video are fictitious and for illustrative purposes only. Assume that in the processing of a wafer, there is a particle machine that does inspections on a device. Though there are other machines that can do a similar inspection, this one is fastest and the most accurate, and hence jobs are processed on it first if there is space available. Otherwise, they are immediately moved to another machine. A machine can inspect up to 2 devices at once. Inspections start and end independently. If no space is available on the machine, the device is immediately moved to another machine. Further, assume that this machine can process up to 2 devices simultaneously, which doesn't necessarily need to start at the same time. The length of time the machine spends processing a job is highly variable, as different jobs may have different inspections required. In this problem, let S equal the service time of a job on the machine. There are many production lines that feed into the inspection machine, and it follows the arrival of devices for inspection follows a Poisson distribution. Arrivals follow a Poisson distribution with an average rate of 4 per hour. The problem is to determine the following. What is the probability an arriving device will be inspected by this machine? In other words, what is the probability the machine will not already be inspecting two devices when a device arrives? If the distribution of service were known, simulating the system under this distribution would be the natural approach. Yet since the service time distribution of jobs is not known in this case, a phase-type approximation of the service process is a good alternative. In general, this approximation may be found by matching moments of the service time distribution to those of the first passage distribution for k exponential phases of service, i.e. the residence time moments for an absorbing continuous time Markov chain. In this case, however, since the square of the mean service time divided by the variance equals an integer, the distribution of service will be an Erlang k, where k is the integer. Let S of k equal service time of a device on the machine. Use the following. It follows that this inspection process may then be modeled as a finite, ergodic, continuous time Markov chain given by the following. The state transition diagram is also given by the following. And the generator matrix is given by the following. The probability that an arriving device will be inspected by this machine is the sum of the limiting probabilities of states 0, 0, 1, 0, and 0, 1, which may be found by setting the Kolmogorov equations to 0 and solving under a norming constraint.